Now?
Yes, go for it.
Okay, sorry for the mess. I'm Miguel Fernández Astudillo. I work in 20 LCA Consultants, and I think this presentation is quite. The ideas here are quite simple compared with others that we have seen today. So here there was just an idea about the assessing the uncertainty of characterization factors related to underspecified archetypes. So let's try to unpack this. LCIA uses often the concept of archetypical scenarios to model the effects of emission. So for example, we can say that a substance X was emitted to air in urban close to ground, or to air in a low population density long term, or simply to air. The first part is what we call in software is usually called the compartment. Some people call it primary context. And the second part is called the subcompartment. What I call underspecified archetypes is the third case where we know that substance X was emitted, but we don't really know if it was emitted to urban air or to an area of low population density, or what. So the idea here is that because characterization factors can vary hugely between different archetypes, using underspecified archetypes may cause important errors that are being unnoticed. So in this example, if we see the effects of human toxicity cancer of cadmium, according to USTOC's implementation in Brightway, we see that if the substance was emitted to agricultural soil, it has a characterization factor of around 480. If it's emitted to industrial soil, it's about 0.8. And in the unspecified case, it's 0.8. Why 0.8 and not something in the middle? It is actually not very well documented, so it was difficult to know. And the idea here is simply define the third case as a probability distribution. And from the other cases, we know that the characterization factor in this case would be between 0.8 and 481. At least we know that. So we could define the third case as a uniform probability distribution between these values, or we could give also some weight to the mode that was given, to the default value that was given to the characterization factor, and define it as a triangular distribution. And how we do this? Well, we can do this with Brightway and a small library that I have on GitHub, freely available. And this library includes some tools to transform existing methods into methods where certain characterization factors are uncertain. And also examples of usage, of use. This is a very simple example. So the library has a few functions, but the main one is this one, cf add uncertainty, which takes as argument the name of a method that we already have in our existing library of methods, and the uncertainty type. Yeah, I think it's 4 for uniform, and I think 3 for triangular. So if we want to use triangular, we just change that parameter, and then we store this as a new method, as you would do in as with the normal procedure, and it's ready to use. I mean, it's as simple as that. And this is an example of the effects for a simple case. So this is the respiratory and organics using the environmental footprint 2.0 for transport passenger train in Germany. And in red, we have the uncertain, the case where we consider the uncertainty characterization factors, and in light blue, the case where we don't include the uncertainty in characterization factors. And we can see that the results are considerably different. and more precisely, the scores are at least 12% lower for 90% of iterations in the case when we consider the uncertain characterization factors. And it also increases the dispersion. And I then thought that we could also model this uncertainty using a discrete probability distribution. So, for example, if we had like a very simple case where we have the characterization factor of particulate matter emitted to air in an urban environment will be 10, and if it's emitted in a rural environment would be 1. So we can say that the unspecified case would be either 1 or 10. We just sample on the possible values, and you could do this. Well, I chose to do this with pre-samples because this is the way I thought could more straightforward to do. And in the absence of better information, I was just assuming that each scenario is equally probable. But if you have more information, you can always do it more accurately. And here we can see the comparison of both cases. So this is the results from the previous slide, where we use continuous probability distributions, and the other one we use discrete probability distributions, and it changed the results considerably. And it has some advantages and disadvantages. I see as an advantage that is closer to how the impact assessment methods were implemented, and it's perhaps more accurate. And it is easy to combine with other sources of uncertainty, such as the geographical variability. As a disadvantage, I see that it's more difficult to operate with. I mean, we need to learn how to use pre-samples. And then I asked myself how this uncertainty affect background LCA databases that we use day to day. And to answer this, what I did is do the inverse of the technosphere matrix and do Monte Carlo iterations, only changing the matrix that contains the characterization factors. And this allows to do calculation for all the activities relatively quickly, which otherwise I think would be quite time consuming. And to measure the effect, I used the mean absolute percentage deviation, which is the difference between the score in the reference case. In this case, the reference case is where we don't use these uncertain characterization factors, and the alternative is where we use them. And it is a measure of the systematic error introduced by not accounting for archetype uncertainty. And this is an example for all the activities in Ecoinvent. You see that the x-axis goes from 0 to 15,000 something, because the number of activities in Ecoinvent 3.6 consequential, and that's the deviation. And you see that certain activities it has a low impact. For other activities, it has a higher impact. And you can see that there are higher deviations in the uniform compared with the triangular, and this is an expected result, actually. And overall, the discrete, uniform, or triangular provide more or less kind of similar results, but bear in mind that the scale in the E it's logarithmic. And if we look to other impact categories like carcinogenic effects, non-carcinogenic effects, and respiratory inorganics, they follow sort of a similar pattern. Some categories show higher errors than others. So the conclusions here is that using undefined archetypes can bias the results in unforeseen ways. Sometimes they will underestimate it, sometimes they will overestimate it. And byte-wise users can account for this uncertainty. I think it's relatively easy to do, at least using continuous probability distributions. And this small library can be used for these purposes. And the continuous case is the easiest case. And for non-Brightway users, I can say that specify the archetype if you have the information, because it can affect a lot of the results. And for method developers, I would say that and software providers that we would need like better documentation of how these characterization factors are actually calculated. The next steps are to add tests and to the code and make it more Pythonic, because right now it's quite ugly. And there's a publication under review, but the preprint is available in an open repository. So if you have any suggestions, please, they are welcome. And well, I'm open to collaboration in any of these ideas. And now it's time for questions or suggestions or opinions. And thanks for your attention. So
Thank you, Miguel. You have a couple of questions. First one from Chaojin. She's asking if you have looked into Ecoinvent activities that have higher variability when the characterization factor variability is taken into account. And if you have you seen any pattern in terms of which type or categories of activity those are?
I had a look and I haven't seen a real pattern. I've seen that activities in new countries or where that I think more kind of recent developments have a higher number of emissions to underspecified archetypes, like for example, new activities in Brazil and so on. But that doesn't necessarily mean that they have a higher uncertainty effect, because this depends on how uncertain the characterization factors are.
Mm.
So I haven't really found any clear pattern on this.
Okay.
And well, I just to say that I sent the list of the most affected substances, the activities to Ecoinvent to see, so they have a look.
Yes. A question from Chris. Could you prioritize the elementary flows which are causing the biggest differences? Maybe we could fix the inventory data itself.
Yeah, but what do we mean by fix? Because we don't really know if I mean, if something, I don't know, if an emission was sent to an just air, maybe there's a reason for that, and maybe not. I mean, maybe they didn't have better information, or maybe they had it and they really didn't think about this. But yeah, without this information, it's a bit difficult to kind of fix ourselves something that was not done by us. But
right. So you're saying maybe the developers of the impact assessment method should be involved as well.
Well, I was just thinking in databases. Sorry, in fix data of on or like maybe I misunderstood the question. So it was about fixing the default values.
Or the underspecified flows in the Technosphere database. Chris, can you be a bit
Yeah,
more?
so what I meant, for example, is if it's really one flow, for example, from this freight train, then, and it's in Germany, if I remember, then you could actually get inventory data on where freight trains go in Germany, plug that into an air model, and say, okay, 25% is actually landing on agricultural soil, 0% is landing on industrial soil, whatever. I mean, these are things that we could learn if we can prove it's important.
Yeah, definitely. I mean, you could use a much more advanced modeling to define the archetypes, and for example, also with better and say like okay, I don't know, 70% was emitted in rural environment, 30% in the urban environment or whatever. Yeah, I mean, there's a lot of possibilities.
And another question from Chris. Any ideas on whether your results would change significantly if we included uncertainty in the input characterization factors themselves?
Sorry, I don't. What do you mean by include uncertainty in the input characterization factors? I mean, the uncertainty is in it's introduced in the characterization factors.
Well, each number, right? Each characterization factor is not a number. It's a distribution, parametric, non-parametric, whatever, right? So if you had, I mean, actually to do this correctly, you would need to get the uncertainty from the LCI IA model, and then you would have a distribution of distributions.
Yes, I haven't done this because I mean, data on uncertainty of characterization factors, if existing, is very scant, and yeah, I haven't really tested this, but I think you could. The easiest way that I see to integrate these different sources of uncertainty is to use pre-samples, but maybe there are other ways. But I haven't really combined different sources of uncertainty in characterization factors, just because, I mean, currently, I think most of the people don't use any uncertainty in characterization factors.